Hi, Craig.
Hi, Craig.
Hello, and welcome back to the paddock. Today is going to be a little bit of a different episode. We are going to do a tech episode with KC. So, on this episode, you're just going to have myself, Hannah, and KC as your main presenter and talker. And we're going to talk all technical things about Formula One. And so, with that, let's go ahead and pass it on over to KC.
First of all, a little disclaimer. I'm not an expert, I don't work in Formula One or anything. I just happen to have a degree in mechanical engineering and find this stuff really interesting. And so I kind of broke it down into just the basics, technical components of an F1 car. So, like the power unit, chassis, suspension, safety, a bunch of different topics that we're going to kind of go over. But first, probably one of the most important parts of the car, as it's what makes it go, is the power unit. So this used to just be the engine, but has evolved to include more components as the cars gain complexity. So the power unit consists of the internal combustion engine, or ICE, and then a turbo with supporting parts, also called ancillaries. The ERS, which is the energy recovery system, so the hybridization part of everything, and then all actuation and control electronics that are necessary to kind of connect them all together and make them all communicate with each other. And there is currently a power unit freeze from 2023 to 2025, which means that the teams aren't really allowed to make any changes to their power units except if it's to help improve their reliability. So now we're going to go on to some engine basics. So in an engine, there's something called a cylinder, and a cylinder is a cylindrical chamber in which a piston, which is like a little disc that fits inside the cylinder, and it moves up and down. The piston moves in what are called strokes. A stroke is when the piston makes a full travel in the cylinder. So it'll start at the top, go down, go back up, or vice versa. And a typical ICE engine uses 4 strokes, which have specific names. The first stroke is called intake, and it's when the piston will move down and an air-fuel mixture is drawn inside of the cylinder. The second is compression, where the piston moves back up and the mix of air and fuel is compressed. The third is combustion, where in a gas engine, a spark plug will ignite the air-fuel mix, creating a mini explosion, and that mini explosion is what pushes the piston back down, creating mechanical work. The fourth is called exhaust, where the now exploded mix of fuel and air is expelled out of the cylinder, and this is repeated. Each piston is connected to something called a crankshaft, which is rotated by the pistons as it moves up and down. Each piston is connected to the crankshaft with a connecting rod, which is very important as it turns the vertical motion of the piston moving up and down into the rotational motion of the crankshaft spinning. This is what powers the car. You might often hear talk of speed in terms of RPM, or revolutions per minute, in reference to an engine, and that's what that spinning is referring to. An F1 engine can technically get up to 20,000 RPM, but as of 2021, it is electronically limited to about 15,000. And so this is way off from like your typical road car. So, the car that you might be driving around will typically be maxed out at around 6,000. But typically if you're like cruising along the highway, maybe like 2 or 3, you can actually see it like on the dashboard of your car. There's a little dial typically that will show you what RPM you're going. But yeah, you're not getting up to 20,000 RPM, in just a normal car. And so current F1 cars use a 4-stroke, 1.6 liter V6 internal combustion engine. So the V6 part of that refers to the number of cylinders, which would be 6, and then the V refers to the shape that these cylinders make. So they physically make the shape of a V, with 3 cylinders on one side and 3 cylinders on the other. So when you see it and it looks like a V, that is a V-shaped engine. And this is also really helpful kind of to understand when you're thinking of the previous F1 engines, like the V8 or the V10, because of the number, that's how many cylinders they had. And that's in a V shape. And the 1.6 liters refers to the engine cubic capacity, which is the amount of air and fuel that can be pushed through the cylinders in the engine. And so these are regulations that are set kind of by the FAA of what the engine can be. So another part of the power unit is the turbocharger. So a turbocharger is a turbine, which is kind of like a fan. Think of a giant wind turbine that you might see alongside of the road that takes wind and converts into electricity. Same concept, but a lot smaller. And so it's a turbine, and then it's also a compressor, both the two combined, that take exhaust air that's coming out from the engine in that exhaust stroke and compressing it before returning it back into the engine. The hot exhaust air that is expelled from the engine spins that turbine, and then the turbine turns another turbine, which, as it spins, sucks in ambient air as well and compresses it before putting it back into the engine to be used for the intake stroke. So putting the compressed air into the cylinder means that more of the fuel mix can be added into the same amount of space in the cylinder, which means that more power can be made. So the turbocharger kind of helps you cram more of that exhaust fuel mixture into the engine than you would typically have if you didn't have a turbocharger. Turbochargers are found on road cars. So it's not like an exclusive, F1 technology here. And they typically have a distinctive sound associated with them too, like a wind or like a spooling up kind of sound. And it's kind of fun to listen to. So I guess if you know your car has one, or you're out and about and a car has a turbocharger in it, kind of listen for that sound of it kind of spooling up and wheeling up.
Yes, as a fellow car enthusiast, I love the sound of turbochargers because they're just so satisfying. If you have the money and you have a sports car, highly recommend it.
I mean, you don't even need a sports car. My little tiny Honda Civic has one. So, yeah, also just kind of a side note, but in the industry, you typically, you want to reduce engine sound, but a lot of the times you don't want to completely get rid of that turbo whine, because when you hear it, you're like, the engine's working, powerfully, it's going great. So you got to kind of balance the cool sounds with maybe the ones you don't want. But so turbochargers are always fun, but as of the more recent F1 regulations, they've added in hybridization. So kind of adding in the electrical energy side of things in combination with the traditional gas engine. So this energy recovery system called the ERS is the main hybrid system of the power unit. And it works by collecting rotational and thermal energy and storing it as electrical energy that can later be reused to give a power boost to the car. So the main components are the motor generator unit kinetic, or the MGU-K, and the motor generator unit H, or the MGU-H, as well as the energy store, which is where all of the energy is stored. It's kind of like a battery. So the MGU-K is an evolution of the KERS system and is an electrical motor that is connected to the crankshaft and the rear wheels that can both store and supply energy. In both cases, it converts kinetic energy into electrical energy. When in recovery mode, it takes the kinetic energy of the crankshaft rotating during braking phases and converts it into electrical energy that is stored. Now, when the MGU-K is in supply mode, it takes that stored energy and uses it to help spin the crankshaft, which helps produce more power. This is similar to how hybrid technology works in a road car. So this is like the traditional unit. And I think also, as of the 2026 regulations, this will be the only hybrid unit. So they're getting rid of the MGU-H for 2026, I believe. And that's because the MGU-H is a lot more complicated. And it's very similar in how it works, but this time it's connected with the turbocharger and is very much an F1 specific technology. And it's located between the turbine and the compressor of the turbocharger, so that when the exhaust gas spins the turbine, it charges the battery, and then when it needs to be used, it uses that energy to spin the compressor. So similar in that it's taking energy that's already kind of in the car, storing it, and then it's able to use that to kind of boost engine performance. So when a driver is on an out lap, or they're getting ready for like a flying lap, they're typically charging up their ERS system. So that way they can use it on the flying lap to help increase their speed. And unlike a road car where you turn a key or you push a button to start the engine, F1 cars must be started with an external device that can be used to start the engine kind of wherever the car is. So the garage area, pit lane, or on the grid. And it kind of looks like a big drill almost. So after the fuel and ignition are turned on, the external starter, which like drill part, spins rapidly into like a connection point and cranks the engine until it starts firing. This is often seen in karting as well, for the same reason as F1 cars, in that it saves a ton of weight on the vehicle. And in racing, if you're able to kind of shave some weight off, that's better for performance. And I actually started go-karts before in college with the starter, and it's not as easy as it looks. You kind of have to have it perfectly matched up, or you can strip the starter end or strip the connection point. And let's just say it's not fun to have to replace that. So you kind of have to be like perfectly aligned, so you're not like tipped up at an angle or, off any bit. It's best, be perfectly aligned. But by not having it as like a permanent part of the car, they're able to save weight and space that it can be allocated elsewhere, especially with the aerodynamics as well. So now we're going to talk about one of the main components where the teams can really kind of execute their technical prowess, which is the transmission. So the main component of the transmission is the gearbox, which transfers torque from the power unit to the drive shafts, which through a lot of complicated connections that I won't go into, turn the wheels and move the car. Basically, what turns the power unit power into movement in the vehicle. So torque is a rotational force that is produced by the power unit and is the power unit's ability to perform work. This is not to be confused with horsepower, which is how fast the power unit can perform the work. Because you'll often hear, horsepower in relation to cars. So the engine spins at a certain speed, or an RPM, that can be too fast for the rest of the driveline to keep up with. So you think of that 20,000 RPM I mentioned earlier, that is very, very fast. And not a lot of things can spin that fast and not break. So to account for this, a transmission is used. Through sets of gears and clutches, the RPM of the engine will be converted to different speeds in the driveline. So I'm going to kind of make a relation to like a bike. So if you've ever rode a multiple speed bike, you have to change gears, or you can change gears. So changing gears changes how much a pedal rotation will move the wheels on a bike. So in a low gear, the rotation of the pedals is much faster than that of the wheels. So it takes more than one full pedal rotation to get you one full rear rotation. In high gear, one rotation of the pedal gets you about one rotation of the wheel, so like a 1-to-1 ratio. You get more torque in low gear than in high gear. This is very, very simplified, but it's kind of how a transmission works in their most simplest form. So it allows for the speed of the car to change while keeping the RPM of the engine constant. And so with constant engine RPM, as you increase the gear, you can increase the speed. And as you decrease the gear, you can decrease the speed. So that's when, you see on the onboard cameras, the drivers hitting the paddle, and you'll see the number go up or down on their little steering wheel screen. They're changing the gears, and they typically go down a gear when they're going into a corner. And they typically go up gears when they're trying to speed up along a straight. So that's related to the transmission. And so a clutch is what is used to actually switch between the gears. So in a normal car, typically the gear that you're in is the active gear, and it helps transfer power from the input shaft from the engine to the output shaft, which turns the wheels. To switch to another gear, the clutch just basically attaches to the active spinning gear that is spinning the shaft, and then simultaneously it will also attach to the gear you're trying to switch, but one that is free spinning, so it's not controlling anything, it's just kind of spinning along. It's there for the ride. And so during the shift, the clutch will get the free spinning gear up to the same speed as the current active gear, and then it will transfer the power to that free spinning gear, so then that gear becomes the new gear that is active and is what is controlling the output rotation. It's very simplified, but it gets a lot more complicated in F1 as the car uses what is called a hydraulic sequential gearbox, where the next gear is engaged while still in the current gear, but without moving the clutch or having a loss of power. This creates what is called a seamless shift, without the jolt you would typically see when shifting gears. So it's similar to a CVT, a continuous variable transmission, and then it's like a seamless shift between them. But unlike the CVT, it still has the traditional, like you do have different gears. You are shifting between very specific gears. It's just a very seamless shift. This technology is super confidential and is typically closely guarded by the teams.
I just want to say if they can share that secret with me, I would love that on a motorcycle. So, like, let me know because that would make my life so much easier every time I ride because you got the clutch in the hand, the gear in the foot, the brake in the other foot, and the brake in the other hand. Like, give a girl a break.
Oh, yeah. It's especially because, to change gears, all you got to do is just, flip a little paddle on the steering wheel, which is a lot simpler than any manual transmission, car or motorcycle, where you have to, like, engage the clutch. There's, like, another paddle involved, like, way more complicated.
They
So
don't even have to do a clutch. Like, you don't have to engage.
they
What?
only actually engage the clutch when they start a race.
So lucky.
Yeah, so maybe they can hook you up with a very expensive and fancy motorcycle that has a hydraulic sequential gearbox. But that's kind of a very basic and simplified what makes up a power unit that powers the car. So the engine, the transmission, the turbo, the ERS all work together to help, throw these cars around track at over 200 miles per hour. But another very important part of that is aerodynamics. You hear it all the time, aero this, aero regulation that, wind tunnel testing, all sorts of things. Aerodynamics is the study of the properties of moving air and the interaction between the air and the solid bodies moving through it. And it's a crucial part of modern F1 cars. Aerodynamic components, or bodywork, are all of the parts of the car that are in contact with the external airstream, which is the flow of air around the car. So basically, any part of the car that comes in contact with the air as it's, driving around. So the car is designed to slice through the air and to minimize drag, which slows you down. Drag is the force of the air pushing back against the car as it pushes forward, air resistance. If you've ever held your hand out of a moving car window, you can feel the difference in how the air pushes against it when it's raised like you're going for a high five versus when it's laid flat like you would put it on a table. That force is drag and is what slows the car down on the straights. The more surface area that is perpendicular to the airflow, the more drag. So in F1, low drag is ideal if you want to go fast. Another important force to mention when talking about aerodynamics is downforce, which is the vertical component of the aerodynamic forces that is responsible for pushing the car down, physically down onto the track, hence the name downforce. This force allows for more traction and grip with the tires, which leads to better control on the track and a higher speed in the corners. This means high downforce is often preferred. Now, increasing the downforce causes an increase in drag, which isn't great when you want high downforce, but you want low drag, but as you increase one, you increase the other. This relationship means you can't really have one without the other, and finding a perfect balance between the two is one of the keys to making a successful car. Aerodynamic components work best in what is called clean air. This is air that is not disturbed and allows for laminar flow, which is smooth, think straight lines, the air moving in straight lines. And this is what helps create downforce. Turbulent air is the opposite of laminar, and it's like spirals, curls, air, very chaotic. And it actually prevents the aerodynamic components from working as they intended because they are designed for laminar flow. The car will leave a wake of turbulent air behind it as it kind of punches through the air, and this is what's called dirty air. It is the dirty air that can cause the car behind to lose performance and can make close racing very difficult. That's what some of the regulations they've been trying to decrease, that amount of dirty air to help enable closer racing again. So two cars can basically battle it out a lot closer on track if there's less dirty air from the car behind. And so now on to, I guess, the major aero components. So these would include the front and rear wings, the bodywork, the floor, and the diffuser. The front wing of the car is the first part of the car that comes in contact with the air and helps to generate around 40% of the downforce of the car. It does this by acting as an upside-down plane wing. This wing shape, an aerofoil, is designed to generate lift on a plane to get it off the ground, so when you flip that shape upside down, instead of pushing the structure upward, it will push it downwards, which downforce, what we want. It's also designed to direct the airflow to specific places on the car to help with cooling and aerodynamic performance. The rear wing on the car works in similar fashion to generate downforce and to stabilize the car to make sure the rear of the car has good grip and doesn't slide around. The rear wing is also what contains the DRS. So the DRS, or the drag reduction system, is a system that the driver can activate to temporarily reduce drag, allowing for increased speeds. The trade-off is that this lowers the downforce at the same time. And it's a flap in the rear wing that, when it's closed, is flush with the rest of the panel and allows for air to push down on the wing. But when this flap is opened, this gap allows air to flow through the wing instead of pressing it down, lowering the drag and lowering the downforce. The bodywork of the car is what gives it the streamlined shape that slices through the air and directs the air going around the car. One part of this is the side pods, which we have heard a lot about this season, as Mercedes at the first decided to just not have them. They actually help to contain part of the cooling system and direct air into the power unit to help cool down hot components and help prevent overheating. Another part is what we call the Coke bottle region of the car, simply because it looks like a Coke bottle if you're looking at it from above. It kind of narrows behind the driver towards the rear in the Coke bottle shape. This shape helps create an area of low pressure, which causes the surrounding air to kind of rush in. This incoming air helps to create more downforce as it interacts with air exiting the diffuser, which I'll talk about in a second. When it comes to air pressure, think of it kind of like temperature, where high will go to low to try to find an equilibrium. So higher pressure air will rush to lower pressure zones. And now to explain the next components, we need to do a quick detour to explain something called ground effect. So in super simple terms, ground effect is how the air reacts when an object is moving very close to the ground. Using Bernoulli's principle, as the area under the car decreases, think of a pipe narrowing in diameter. This causes the air to speed up and in turn create a low pressure zone, which combined with regular airflow above helps to create downforce. It basically acts as a vacuum that pulls the car down onto the track. But if that seal of air is broken and turbulent air is allowed to mix in, it can cause a sudden drop of downforce. This complicated but important phenomenon was first introduced to F1 cars in the 80s and was discovered almost by accident. But tech regulations were put in place to limit its effects due to safety. As I mentioned, that if that seal is broken and you get that sudden drop of downforce, that means you can very easily lose control of the car and can cause a lot. And it did cause a lot of serious accidents back when this kind of was first brought into F1. So they kind of limited the effects, but it is back as of the 2022 regulations in the forefront. So the shape of the floor is key to being able to use ground effect to your advantage. And thanks to Checo and Lewis crashing in Monaco, we had a lovely view of two different teams' approaches to floor design. And then I think we've seen several other floors as the season has gone by. You know, you saw how complicated the Red Bull floor was and how detailed and how crazy that looked. And then you saw Williams, which was basically flat. So every team does it differently. And let's just say if you wonder how important ground effect and all of this can be, Adrian Newey's university thesis was on ground effect. And we can all see how his impact on the performance of the Red Bull car has gone. So in combo with the floor, which is, you know, the main part of this, is also something called the diffuser. It's what's located on the back of the car. So if you look at the back, it's that little bit towards the ground underneath the wing. And it works in coordination with the floor to help create more downforce, which is honestly, everything is designed to help, you know, create more downforce. And so the shape of the diffuser will widen and help transition and direct that fast-moving air from underneath the floor to the surroundings. And direct it in a way where it doesn't, you know, that transition from like really fast, very tight to just the open atmosphere. They want to try and control that as best as they can. And since on-track testing in modern F1 is extremely limited. Teams will often use wind tunnel testing and CFD, which is computational fluid dynamics, to help engineer their aero parts to see if they will be effective on track. So CFD takes a model and then simulates and analyzes the fluid flows, which air, how that interacts with the model. And then the simulation data can then be compared to data from the wind tunnel, which is just a giant tunnel with a big fan that can simulate, I guess, a car driving on track or on the road where the wind rushes by, but in a controlled environment where you can control the speed and you can kind of control to make sure it's laminar flow versus if you just go onto the highway, you can have a gust of wind here or there and other cars going by, but this is just a very controlled environment. And so they're actually able to take CFD data and compare it to the wind tunnel data to help correlate the two. So basically, if you see a certain result in CFD, it will mean this in the tunnel and the track and, vice versa and everything. And another thing to consider is that relationship between drag and downforce. So each circuit has a different layout, and teams will adjust that balance of those two forces as such. So if a circuit has more long straights where, speed is more important, the balance might shift where you might have, less drag and less downforce. But maybe in a circuit where control in the corners is really important, the team might go for a more downforce heavy balance. So it's really up to the team for that specific, circuit, the driver, everything like that. So enough about aerodynamics, and now we are on to the chassis. The chassis is the core of the F1 car, almost literally, because it's in the very, very center, in the very middle. And it contains the driver and is the structure in which almost all of the other components somehow attach to. And it must be very strong and stiff structure that can withstand the different loads that are coming from the suspension, powertrain, aerodynamic parts, or be able to withstand a potential crash. It is also called a monocoque or a survival cell, since it also serves to protect the driver. It undergoes extensive testing to make sure it meets all FAA safety requirements, but for good reason, as modern chassis offer much more protection to drivers than F1 cars of the past. This structure also holds the fuel bladder, which sits behind the driver, so the structure's designed to kind of help prevent that bladder from being punctured or prevent any fuel leaks, because in the case of a crash, you don't want fuel leaking everywhere to cause a fire. And so the chassis is typically one of the first components that is designed due to how integral it is to the design of all the other components. So the Aero, the bodywork needs to be able to fit on the chassis, the engine and transmission needs to attach properly, suspension needs to attach properly as well. So typically it's the first thing that is kind of finalized or designed for next year's car. So a lot of the teams have probably already started working on or are getting close to finalizing, their chassis development for the 2024 car. So one of the main things that links to the chassis is something called the suspension. So the suspension is what links the car to the wheels and is an important part of ride and handling. It consists of 6 structural members per wheel. These structures are 2 double wishbones, a push or pull rod, depending on what the team decides, and a steering arm or track rod, depending on if it's located on the front or the back axle. Think of how your car responds when you go over a bumpy road or when you turn the steering wheel or you brake. When you're driving at 200 miles per hour, you want the car to respond well and quickly to when you put driver input into it. So when you're turning, when you're braking, you want it to respond the way you intend it to. And this also ties in with aero, as if your car is moving up and down because of a bumpy road, that will change how effective the aero components are. As well as the obvious part that the suspension is in the path of the airflow, that will also affect the aerodynamics and must be considered. And if you hear talk about setup, that is often referring to changes that can be made to the suspension to suit a driver or a specific track. So this includes, but is not limited to, the camber, which is the tilt of the tires in or out, looking from the front or back of the car. Toe, which is the tilt of the tires in or out when you're looking from the top of the car looking down. Spring rate, which is how stiff of a suspension you want. And ride height, which is how high off the ground the car is. All of these things can be slightly adjusted for preference and to maximize performance of the car. So you can't really talk about technology in F1 with talking about all of the safety aspects of it. So one of these is actually the radios. So F1 first started using radios in the 1980s, and they have become an important tool for both information and for safety. It allows the drivers to communicate with their race engineer while driving. This could include things like current lap times, gaps to other drivers, traffic on track, and suggested settings. And if the radio is still working after an accident, it also allows the team to quickly confirm if their driver is okay. To speak, the driver will press a button on the steering wheel and will wear an earpiece in their ears underneath the helmet. All communications must be open and accessible to the FAA and broadcasters, so teams will try to maybe use code words or kind of hide their sensitive information or not say too much regarding strategy so that way other teams can't, figure out what they're doing. Modern F1 cars are also chock full of sensors and data recorders that are constantly sending feedback to the engineers. This is often called telemetry. This includes information such as speed, engine RPM, fuel, tire pressure, and temperatures throughout the car, including the tire temps, as overheating can be a problem pretty much everywhere on an F1 car. They use this data to help optimize performance, but to also make sure all systems are working properly. So when a driver has a collision or hits a curb or runs over some debris, the engineers can take a quick look at the data to make sure the car is still drivable and that the driver doesn't need to come into the pits for, a front wing change or new tires or something like that. All of this data is also analyzed to help determine race strategy to try and get the maximum performance. All of the cars are also hooked up with GPS and cameras that come in handy to the teams as well as to the viewer. GPS is important so safety crews can get to the car as soon as possible, or teams can let the drivers know about traffic coming up. This is especially important as in qualifying, you can get penalties for impeding where you're blocking drivers on track. And to help avoid this, the teams will communicate, hey, this person's coming up behind you really quick on a flyer, you need to get out of the way, or, there's traffic ahead that you need to, watch out for and avoid. The cameras also provide a good live view of what is happening on each car on the track. These onboard cameras come in especially handy when trying to see what happened after a chaotic start or a collision, and you can often get multiple views from different positions depending on where the cars are on the track. To help with accident analysis, specific equipment is required on the car and on the driver. The car must be affixed with one FAA Accident Data Recorder, ADR, and it's kind of like a black box of an airplane to record data. It also must have 2 accelerometers to measure acceleration, which is the rate of change of velocity and is often correlated with g-forces, and a high-speed camera. The driver must wear in-ear accelerometers to measure g-forces as well as biometric gloves. The in-ear accelerometers are important to measure for basically how much g-force the body is withstanding, and the biometric gloves can give feedback on the driver to the team and to the medical staff. In addition, an FIA marshalling system, which is a car positioning system, and bidirectional race control to car comm system is in place. Track signal, info display, and a medical warning system must also be fitted onto the car. So oftentimes, like when a yellow flag or red flag happens, it will be able to pop up on the driver's steering wheel to let them know, hey, there's, a yellow flag or a red flag, be cautious or, come back to the pits. An important thing when it comes to driver safety is something called g-force, which is the force per unit mass due to gravity at the Earth's surface. So the number in front of the g is how many times heavier your body will feel. So 2g is about 2 times heavier, and 9g would be 9 times heavier. Most humans can withstand up to 4 to 6 g's for a very short amount of time. Specially trained fighter pilots can withstand 9 g's for about a second or two, but sustaining anything above 6 g's would probably be fatal, and even sustaining 4 g's for more than a few seconds can risk you blacking out. That makes the g-forces that F1 drivers deal with even more impressive. They mainly deal with lateral g-forces, so forward, backward, left, and right, and can pull the blood from your head to your extremities. This often occurs during accelerating, braking, and turning. During cornering, drivers can experience between 4 to 6 g's, just every turn, which is a lot to withstand if the human body isn't really designed to. The human body is, pretty handy, and it can survive very short bursts of g-forces, even in the 100 g's. But it's just any kind of long-term exposure to that can kill you, basically. During crashes, when the car abruptly stops, the drivers can experience very high g-forces. So during Max Verstappen's crash in Silverstone of 2021, He experienced around 51 Gs, which would basically be like feeling 51 times heavier than you normally are, just for a split second. And then Roman Grosjean's crash recorded forces of up to 67 Gs. And Jules Bianchi's fatal crash at the 2014 Japanese Grand Prix recorded G-forces of up to 254. These forces are one of the reasons the drivers must be so physically fit, and their potential danger is the reason why they are measured for both the car and the driver. This is also the reason why drivers have very strong necks and do a lot of strength training exercises focusing on their neck, is to help withstand those G-forces that push their head around in the car. So a strong neck means you're able to keep your head straight and looking straight on, and so you have your full range of vision in the car. And a lot of drivers have mentioned, if they are getting in the car after a really long time, or, they've never been in a car before, that their neck gets really, really sore after they do a race. And we'll finish up with probably one of the most famous safety devices that was added most recently, the halo. And it's probably one of the most important safety features that has been added to F1. So the halo is a titanium bar that is securely fixed to the chassis. It surrounds the driver's head. This relatively small bar must be able to withstand forces of 125 kilonewtons from multiple different angles. While this device does affect the aero and the aesthetics of the car, that's nothing compared to how much the halo has already done to save the lives of countless drivers. So consider accidents like Fernando Alonso launching over Charles Leclerc in Spa in 2018, Roman Grosjean's terrible accident in Bahrain 2020, and the crash between Lewis and Max at the 2021 Italian GP, where Max's wheel kind of landed on top of Lewis's car. And if the halo hadn't been there, you can only imagine what would have happened. And of course, Zhou Guanyu's crash at Silverstone last year, where the car slid upside down, scraping the halo and into the barrier. And I think the roll bar in that case actually failed. So if it hadn't been for the halo, there would have been nothing to protect the driver at all. So halo is probably one of the best additions to safety in modern F1. Because all of these crashes, would have likely resulted in serious injury or even death if it hadn't been for the halo. And it's just this small little titanium bar that attaches to the car. But there's a lot to go with the technology in an F1 car, and there's definitely more to talk about. But hopefully this was just a kind of a basic, Tech 101 of the main components of an F1 car, from the powertrain to the chassis to even some of the safety features. And hopefully you guys learned something today about how an F1 car works.
In reference back to what you said about the halo, one thing I've always been very inquisitive about is talking to drivers who had been there pre-halo, who are still drivers now with the new halo. While it's definitely amazing from a safety standpoint, what was some of the adjustments that they had to make with that new halo as far as like viewing impairment, or just the adjusting of like how they had to do that with the new regulations of adding it? I've always wanted to ask a driver that.
Yeah, I think honestly one of the main differences that they had to get used to was getting out of the car. Because suddenly you have this structure that it was like an open cockpit, and now you have this structure that makes it a little more difficult. But they have like that training they have to do where they can prove they can get out of the car within like a certain amount of time. So I think it just took a lot of practice. But I mean, we do have a lot of drivers in the grid that were in pre-Halo and I guess post-Halo, you can call it. But
Yeah,
then some drivers, it's all they've ever known. The grid's only getting
exactly.
younger, so
Exactly. I don't know if I ever got the opportunity to ask the driver and it would get approved by their marketing team. I would so ask it. It's one of those questions where like I feel like they don't want to talk about it because they don't want drivers to go in like tangents, but I feel like it would be cool to ask.
yeah, I mean, definitely there's like a PR side of everything.
Mm-hmm.
When it kind of comes to everything nowadays, but honestly, it would just be interesting to hear the F1 drivers just kind of their opinion on more of just the technical side of things at all. Like, how much do they know? How much, like,
Yes.
Do they input? Does it help them be a better driver if they know more about, like, the technical side of things? Like, maybe with the setup? Like, I don't know.
And do they get into it and learn it so when they're developing the car next year, they can add their input of like make adjustments with this, make adjustments with that, with the technical regulations to like make the car better? Or do they just trust the engineers and everything to just do good and then just tell them, this, that? You know what I mean? In the feedback
Yeah.
sessions after the race and quali and testing.
I'm sure, like, some drivers, because I think, wasn't it Sebastian Vettel was known for, like, very, very long debrief sessions? Curious as to, if he had a lot of technical background, if that he was able to just go on about exactly what he wanted. I guess it definitely, I think, helps you be very specific about what you're talking about in a way that the engineers can take your feedback and actually implement it on the car. But I think part of it also is just, how you feel as a driver when you're driving around. Like, oh yeah, this corner felt bad. But you need to be able to, like, explain that in a way that
like
it can
you
actually
had
be...
trouble braking or
Yeah.
Yeah, so they have to know some type of terminology / knowledge of it to be able to talk to their engineers, I feel like. Because I would be like,
Yeah.
I couldn't brake, so like I couldn't turn.
And it's crazy because, like, a lot of them didn't have a traditional education, I would say, because they were racing.
Right.
So, like, where did they get it? Did they just kind of, like, pick it up on the job over the years? Or have they
Probably.
actually, like, spent time, maybe taking, like, a little course here or there? Or
Reading a
if it's just...
handbook.
Yeah, reading the instruction manual. God, I can only imagine the instruction manual of a F1 car would be like
And an
a
F1
foot.
driver.
Oh boy.
The F1 driver's here. The F1 car's here.
Honestly, it's probably taller than some of the drivers are.
Probably. And with that, we're going to move on to our pre-outro, and today's going to be a motorsport fun fact of the day. So this is just something I quickly found that references Mark Webber had once said that Formula One is a very one-dimensional in terms and what they actually do in the cockpit. So that just basically tells you you never fully know what's going on behind the scenes, and there's a lot, like Casey had mentioned, from a technical standpoint of what the car is made out of that you don't know, that you don't get to see on like a day-to-day basis. So that's pretty cool. And with that, I love learning more, especially about technical regulations and getting to see how that kind of works from an F1 standpoint to just a regular car. And I hope you did too. So let us know on our socials. Everywhere we are Paddock Girls Podcast, except Twitter. You can find us at Paddock Girls Pod. And also, don't forget to share, rate, and review the podcast wherever you listen, like Apple Podcasts or Spotify, and now on TikTok. Thank you so much for joining us in the paddock. See you next time. Bye, Craig.
Bye, Craig.